So in today's talk, I'll be exploring the interplay between measuring quantum states and getting interesting topological quantum states. So for many decades now, right, theoretically at least, it has been appreciated that if you have a relatively simple Hilbert space of just qubits on a lattice, if you have enough entanglement in that space, you can effectively get immersion properties that are much more exotic than the underlying qubits. For example, gauge theories might emerge as effective low-energy descriptions. Or you might have the emergence of quasi-particles with generalized exchange statistics called anyons, or you might have robust topological ground state degeneracy, all kinds of interesting emergent phenomena. This kind of concept is related to a variety of different aspects in physics. So, for example, these emergent features in entangled quantum states can be relevant for understanding quantum materials at low temperatures. But also these emergent properties are so interesting and powerful that they might actually be ultimately relevant for what we usually think of as fundamental physics, right? Perhaps space-time continuum or fundamental model of particle physics might itself be such an emergent phenomenon due to quantum entanglement. And on the more practical, or at least applied front, these emergent properties might eventually one day be used to store and manipulate quantum information if we get to dream a bit. So there's a variety of reasons to try to perhaps see if we can create these entangled states in the lab, right? And in recent times, there's a kind of new game in town where we can start exploring these excited entangled states. Basically, these kind of quantum devices that are being developed in labs across the world, all kinds of different types of devices or platforms or simulators, whatever you might want to call them. For example, atoms trapped in optical lattices, right? Or we also just heard a talk about superconducting qubit chips and the like, maybe cold ions, etc. And what all these different amazing platforms have in common is that if you compare them, say, to conventional quantum materials that we dig out of the ground and cool down, and these kind of novel quantum devices, you provide a lot of insight into what your system actually is about. Basically, where do the effective qubits live? What are their interactions? And instead of just having passive knowledge, you also have a lot of control. You might be able to choose where the effective qubits live, when they interact, and how strongly they interact. And also, you really get to probe your quantum state in novel ways. And some of these devices, you can really measure your whole wave function, all the qubits at once, to get access to multi-body correlation functions to really get insight into these emergent properties that you might want to get. So it's kind of a very natural question to wonder, can we use these kind of platforms to realize and explore these entangled states and their emergent properties? And just to give an example of two relatively recent developments in that direction, about in the attempt of trying to realize such types of emergent gauge theories. So, for example, one platform is at Rydberg atom tweezer arrays, where one tries to realize it, say, as a low-energy property, as the low-energy physics of a certain Hamiltonian. Or an alternative is kind of the more digital approach, where you try to build these interesting entangled states, like the toric code wave function, by using unitary gates, the right being on a superconducting qubit processor from Google. Right, so it's kind of complementary approaches that can be used to try to create these entangled states. And while these experiments are very encouraging, they also interestingly highlight some puzzles or challenges for future experiments. Basically, the timescales involved. Right? So, for example, even though the approaches were quite different, what they have in common is that they're both unitary. For example, in one case, one tries to realize low-energy states with respect to some Hamiltonian. So in practice, one tries to adiabatically prepare the state by starting in a simpler state and trying to sweep slow enough. And in fact, it turns out if you have to tune to a quantum phase transition, you actually have to go parametrically slow in system size, which in that actual experiment I just mentioned was the reason that it actually turned out one doesn't quite prepare the ground state, but a non-equilibrium state. So there, timing is an issue. But also, for example, if you think of the digital approach where you use unitary circuits, it's known that for an exotic state like the toric code, the circuit depth will grow with system size. So if one tries to do it for bigger systems, one eventually inevitably runs into issues with having a finite coherence time in your system. Okay, so there's a natural question of how do we prepare these interesting states and explore them efficiently without eating up all the time or even just not getting the job done at all in the available time. The reason that both of these approaches scale with system size, the necessary time scaling with system size, is not an accident. It's really a fundamental aspect of these states of matter. In fact, if you think of the realm of all possible many-body quantum states, you can roughly order them in the degree of entanglement that they have. And the interesting types that we're discussing in the context of this talk, with the ones with emergent gauge theories and anyons and whatnot, they exhibit so-called topological order. And this exotic property means that if you try to create these states, say by using unitary circuits, the circuit has to be roughly as deep as the system is wide. Okay? So it's really a fundamental constraint that you can prove just based on locality of interactions and unitarity of the methods. So in summary, if you're trying to create, say, something called a toric code state, which has all these interesting emergent properties, it's known that you really cannot do it by starting with, say, a product state and only having a finite depth unitary circuit. Okay, so that seems like a fundamental problem, right? Because any system has a finite coherence time, so if you have enough qubits, it seems maybe certain states you simply cannot create. But yes?
General statement if you have the long range.
Good. Good. Yeah, that's a good question. So here, the way I was talking is that I'm assuming physically local interactions. Then, for example, the depth really is linear. If you allow yourself two-body but long range, it still scales with system size, but not as fast as linear. But it still doesn't resolve the issue as such. It just makes it a bit better, but the fundamental issue remains. Yeah, thanks. Good. So it's really a fundamental constraint imposed by unitarity and locality. We're not going to violate locality here, but we will try to violate unitarity. Right? Indeed, quantum physics allows for wave function collapse, right? And that process, of course, is not unitary. It doesn't preserve the norm of the wave function. And so one can wonder, can that process be used to speed things up, right? Trying to avoid a unitarity constraint. Or, of course, if you prefer the many worlds interpretation, you're somehow entangling yourself with the wave function. Either way, something drastic happens, and then you could ask, can that drastic change help you? And it has been appreciated, at least theoretically, that for certain states it is possible. For example, if you try to create a particular state of matter called the toric code state, even though it's impossible in finite depth with only unitary circuits, you can do it in finite time if you also use wave function collapse to your advantage. Okay, so just to give you a bit of an intuition for why should wave function collapse speed things up that dramatically. So I was already referring to something called the toric code state. So for concreteness, it's actually the ground state of this spin Hamiltonian, right? We think of spin halves living on the links of the square lattice. There's these four-body interactions shown there, some four-body Pauli Z and four-body Pauli X interactions. And the ground state of this Hamiltonian is known to be very exotic. It has these emergent gauge fields, emergent anyons, and could potentially be used to, as a surface code and could be used to store topological information. So that is an example of a state we would like to be able to create. Okay? Basically, the state that's left invariant under both of those stabilizers, they're called. Now, how can you create this with measurement? Well, actually, it's a one-line argument. You can check that all those terms commute. Basically, just measure all of those terms in the Hamiltonian. And since they commute, you can do it in finite time all at once. So just to flesh it out a bit more, okay? So imagine starting with a product state of qubits that are in a product state in the x basis on the links of the square lattice. This is a nice choice because actually you can check half the terms in the Hamiltonian are already happy. Right? If you act as four-body term, it's actually +1. Of course, it doesn't respect this other four-body term. In particular, this state is not an eigenstate of that. So it's not a toric code state. It's an unentangled, boring state. So now, just to get the other term in the Hamiltonian happy, simply measure it. Right? It's a four-body observable. You can measure it in your quantum state. And of course, right, measurement projects you into an eigenstate. That's kind of almost the definition of a measurement. And if the measurement outcome is 1, there's two possible eigenvalues. If it is 1, you can show that it uniquely gives you the toric code state. Okay? So, and you can do that all at once because they all commute. You can check it, you can work out the details. But of course, measurement is random. You might get -1. We say the so-called, whenever you have a vertex where the measurement outcome is -1, the parlance is that you have a E-anyon. But basically, you can convince yourself that once you know where you get -1s, after a bunch of spin flips, a product state of Pauli X spin flips, you can kind of pair them up. And basically, the upshot is you can clean up any measurement outcome that's not +1, and you can always deterministically bring it back to the all +1 state. Okay? So this way, you can in finite time, prepare, in finite quantum time, so to speak, prepare a toric code state. Yeah?
Time also hold if you take into account the classical propagation.
Good, that's why I said quantum time. Exactly. What you actually do is you push all the non-locality in the classical channel, because when I glibly said, oh, you can pair up all the minus ones, you need to know where the minus ones are. And that, of course, requires a long-range classical information gathering.
Well, maybe not.
It will. No, it will. Yeah, I can.
Will it?
Yes, because you can always kind of push everything into the. Anything you can classically do, you can make it quantum. I guess not quantify, that's wrong, but whatever. You can write a circuit that would have done it in a purely quantum way, but then you would have get a violation with known no-goes.
I see. So you say you could take all the classical stuff, make it quantum, and then you would violate no-goes.
Yeah. And you can even write down a proof. I think we did it in one of our works where you can prove that if you only do local post-processing, you actually can do stuff like this.
Okay.
There's a more precise phrasing, but that's the upshot.
Thanks.
Good. So yeah, and hence you have to do a non-local classical information gathering, but there's really a meaningful distinction between quantum time and classical time in the sense that you could ask quantum operation-wise, do you always need finite time, and indeed also in practice that's kind of the costly piece, right? At least as long as we're not doing things at other ends of Earth or something like that. At that point, you start to worry also about the classical time. Okay, good. So you can prepare these states in finite time, in principle, and that has been appreciated theoretically. But then a question is, well, two questions that we were wondering about. So although this method was known theoretically, you could ask, can this actually be done with, say, the current existing quantum devices, or is it still a bit of science fiction, so to speak? And secondly, it works for a particular type of state, say called the toric code state, but we know there's many different types of interesting so-called topological states. You could ask, how broadly does this work? What kind of states can you prepare with measurement? What states can you not? Does it tell us something deeper about many-body entanglement? So that brings us, those two questions are the theme of today's talk. So in the first part, I'll actually show you some recent experimental data showing that you can, with existing devices, create certain topological states using measurement and kind of classical non-locality, so to speak. And in the second part of this talk, we'll explore more theoretically what is the more general concept and ability that you could, what does measurement buy you, and what is still impossible, okay? And we'll explore these topics there. Does that sound good? Any questions so far? Good. So let's start with an actual recent experiment that tries to implement this kind of preparation protocol using measurements. And this is a large collaboration of people, actually some of them sitting here in the audience. And also particularly want to highlight Mohsin Iqbal and Hendrik Dreyer, who really put a lot of hard work into this, making this an experimental fact. And so what I'll be exploring, so I should mention this is a collaboration with Quantinium, which is a cold ion platform. Okay, and so using that cold ion device, we'll try to create the toric code state with a finite time protocol using measurement. Okay, and I should mention before, I was showing the toric code with qubits living on the links of the square lattice, as you see there. Just for convenience, to match also the little pictures we have here, imagine rotating the lattice by 45 degrees, so they now form a square lattice of themselves, so now they live on the vertices of that smaller square lattice. And now you see that basically every other plaquette is a plaquette of the original lattice, where the other types of plaquettes were vertices of the original lattice. Okay, and what we're going to do is really the story I already mentioned before. So again, we're going to start with the product state on the vertices of the square lattice. We're actually going to be using an effective torus geometry. Then we're going to measure every other plaquette. So we should mention the product state already has this nice stabilizer property, but we would like to have every other plaquette to have this stabilizer property. If you have both of those on alternating plaquettes, you have the toric code state with all the interesting properties. So we're simply going to measure this 4-body observable on every other plaquette. And again, the measurement outcome is, of course, random. You might get 1 or -1. That's what these yellow and black plaquettes show. But then we actually use active feed-forward, where we get the information of the outcomes, and then we decide which quantum operators to apply in our circuit to deterministically try to prepare the clean toric code state. Is that clear? Okay, so as you might guess, this is an artist depiction. The system is not quite that huge. Here's the actual system result. It's kind of the same thing. And there's actually periodic boundary conditions here. But so basically, we're pairing a toric code on a 4x4 kind of little torus. Yeah, if you draw this as a torus, it looks a bit sad, but it's essentially this. And it's for these system sizes, you could probably just use unitary methods as well. But it's nice to at least use a protocol which would, the protocol itself is independent of system size. Okay. So basically, this is the experimental outcome of doing exactly the steps I just mentioned. And here I'm plotting the expectation values that you afterwards measure over a quantum state. If we hit the ideal toric code, all these numbers would be 1. Of course, reality makes them slightly smaller, but you still get kind of close. And we also we also measured the topological entanglement entropy. Just in the interest of time, I didn't include a slide about that.
Ruben,
do
you actually have periodic boundary conditions in the experiment?
Good question. Effectively, yes. Physically, what's happening, these ions in the current devices are still arranged on a line in a trap. Mm-hmm. But in the continuum computer, you can really move the ions super fast, and you can move them past each other. And that time scale is much quicker than the kind of, the quantum times we're kind of worried about. Basically, in the runtime of the circuit, we can even get to neglect the effect of moving the ions around. But in other words, in the runtime of the experiment, it's effectively an all-to-all connectivity. And in particular, of course, you can do a torus connectivity if you like, which we literally, indeed, implemented, so to speak. Yeah.
Mm-hmm. But you don't get extra sources of decoherence from moving the ions around?
Well, in principle, yeah, that'll definitely be there, but they're definitely not the dominant ones. We can, to a good degree, neglect them in the currents. Mike should correct me if I'm saying anything not kosher, but yeah, that's my understanding. And it's interesting that if you look at Quantinuum website, the future plans really are to also actually, go to 2D eventually. But in current devices, it probably wouldn't have any, it's small enough that you can actually do the shuttling quick enough that you can have an all-to-all connectivity. Thanks for the question. Let's just check. So the clock, that was, at which time should I stop? Maybe that's a practical question.
It's counting down, and that includes your question.
Yeah, okay, good. So 15 minutes, I should stop. Good. And then I had one slide just to show the kind of games you can play once you can create these toric code states. For example, don't really want to go too much into detail, but you can also create a toric code on lattices with dislocation defects, and that's interesting for a variety of reasons. Those defects turn out to have non-abelian properties. What that means is that if you create certain types of anyons that come with a so-called M label, if you move them around the defect, they can basically change their anyon type. So you can play these kind of fun games with these toric code type states. Okay, so that's all I wanted to say about the experiment as such. It's kind of a proof of principle that some of these devices can actually create topological states via measurement, which perhaps all the more motivates the fun theoretical question of what is in principle possible. Personally, maybe already interested just for conceptual purposes, but knowing we can actually do these things, perhaps we should figure it out, what's possible and not. And that leads us to the second and last part of this talk, which is in that second part of the talk, I'll try to convey a more general perspective and a more general kind of protocol, of which the previous toric code thing is but a small example. Okay. In particular, with Nathan Devasarakan, Ryan Torngren, and Ashwin Vishwanath, we found basically a more generalized perspective where using measurements and feed forward in finite time, we can implement a map that goes by different names. Some might call it the gauging transformation or the Kramers-Vanier transformation. As I'll discuss in a moment, this transformation as such mathematically is known for decades, and it's very useful to map models to each other mathematically. So if you solve one model, you secretly solve the other one. But usually it's not thought really as a physically relevant mapping, because it's very exotic in a sense. But it turns out that kind of mapping you can really deterministically implement using measurements and feed forward. And I'll, if time permits, I'll briefly comment also how you can interpret as many-body quantum teleportation. So what is this map or this transformation that I mentioned? So essentially, it's a transformation of quantum states in one Hilbert space into quantum states in another Hilbert space. So for example, these blue dots signify qubits on a squared lattice. And basically, any quantum state you might have on this lattice, as long as there's a global Ising symmetry, there's basically a well-defined map that maps it to a quantum state on this different configuration of qubits living on the links of the square lattice, and the map is very non-local. It's so-called gauging map. As the name suggests, what it involves is the original wave function has a physical symmetry, like say sigma x on all sites, say a symmetry of the system. It will in some sense gauge it. Okay, so what that means, for example, in practice. So here I'm writing down the general, using these rules, you can figure out what any state here maps to on the other end. And just to give you a sense, if you input the simple product state on this lattice, and if you apply this map, okay, the output is the toric code wave function. So that hopefully conveys that this is a very kind of non-trivial map. It creates a lot of entanglement. And conceptually, this is related to the fact that one way of understanding the toric code is as an emergent Z2 gauge theory, okay, similar to the gauge theories we know for fundamental physics, but for a different gauge symmetry. And indeed, that's related to this as a result of the gauging map. That this is a physical symmetry of flipping all the spins, right? It's an eigenstate. And somehow that physical symmetry is morphed into a gauge symmetry, okay? And this works for this particular product state, but it works for any wave function you like with that physical symmetry, okay? So it's basically a general map. You can choose any input state. And this map has been explored in a variety of contexts. It traces back in some sense to the lattice gauge theory works in the 70s, where they tried to use it backwards to solve gauge theories. But because it's very non-local, yeah, right, as you can already see, it maps the product state to a very entangled toric code state. It was, as far as I know, not really thought of as a physical transformation, right? Because in terms of unitary circuits, it would be an absolute mess. But it turns out, using measurement, it's incredibly simple to implement this transformation deterministically. Okay, just to give you a sense, this is using kind of dense network notation here. So with the map we want to implement is, say, from blue qubits, which might live, say, on the sides of the square lattice, to, for example, red qubits, which live on the bonds of the square lattice. And it turns out that the protocol looks something like this. So what is it showing? Let's say time runs from bottom to top. Okay, so we start with our original quantum state on blue. I add some ancillas in red in a product state. Then I do some very shallow entangling circuit of control Z, right? So basically some Ising phase gates. In 1D it will be depth 2. In 3D on square lattice it will be depth 4. Essentially coordination number of your lattice. It's finite, that's the point. And then you measure your original qubits, okay, blue. Here I kind of wrote it as a post-selection, where it's all plus. But as before, it turns out whenever you get minus the other measurement outcome, in finite time you can pair them up, with the classical, setting aside the classic non-locality in the classical channel, and then you have this deterministic protocol for implementing this map. Okay, and let me maybe skip over this, but you can, by kind of doing this pushing through of operators, you can really write very simple proofs for showing that it really has the right transformation of quantum states. So just to give you a sense, suppose you're trying to do it in practice, what would you do? Someone gives you their favorite Z2 symmetric state on the square lattice. Basically, what you would do as an experimentalist to try to gauge it in finite time, right? Just to repeat as we said before, put a product state on the links. You do some control Z on nearest neighbors. Okay, as an aside, if you started with a product state, at this point you would have created some short-range entangled state called the cluster state. The reason people like the cluster state, for one reason, is if you now measure the sites, you'll get the toric code. But that's only in special case where you start with a product state. This could be much more general. And now we have this short-range entangled state. And now we're going to measure the original qubits, which were the blue ones. Okay. And of course, that might give minus ones, right? And then Norbert goes and look where the minus ones are. It takes some non-local classical time. But anyway, we ignore that because Norbert's very fast. And then we flip all the spins connecting minuses. And then it turns out you can prove that this deterministically implements the gauging map. Okay? And in the very special case where you start with a product state, you end up with toric code, but could be more general. Okay. So maybe very briefly, what I just said, you can actually interpret as a non-trivial many-body version of quantum teleportation. Okay, so I just can't resist to briefly mention as like a side comment. Basically, let's first remind ourselves of conventional teleportation. Of course, you can teleport a single qubit. But if someone gives you a wave function many qubits, or like 3, just in a simple picture, you can, of course, do teleportation in parallel, right? So these are some bell pairs, okay? And suppose I want to teleport my wave function from here to here. The usual teleportation protocol is you measure in a joint bell basis of these 2 qubits, and that basically teleports your wave function here. Of course, there's some randomness in the measurement outcome. That classical information needs to go here and do some little fixes, the usual teleportation scheme. That's essentially the idea of right, teleportation. But it turns out there's a second option, which is kind of what I just told you about in the previous few slides, but now rephrased as a teleportation protocol. Someone gives you a wave function, say on one Hilbert space, say qubits on a square lattice. Now you use a different resource state. Instead of a tensor product of Bell pairs, you use something called the cluster state. It's a relatively simple state to prepare. And then we now do Bell pair measurements on every other qubit of the cluster state. And essentially, it teleports a wave function on the other qubits. But in addition to teleporting it, it has applied this gauging map or Kramers-Wanier transformation. And again, the randomness of measurement, you need to, you need to bring that classical information to here and update it. But again, very similar to the usual teleportation protocol. Good. So apparently we can do this kind of fun many-body teleportation, or in other words, applying the gauging map. But what does it really buy us? Okay? I try to convey that a toric code is but one special case. But what is something that it really buys us? Well, it turns out there's a hierarchy of interesting kind of topological states. And the toric code is the simplest flavor, right? The vanilla flavor of topological states, the so-called abelian. It's a particular simple property of the emergent quasi-particles. But it's known that there's more exotic non-abelian states possible, which have more exotic properties when you braid them around each other. In terms of gauge theories, they have an emergent non-abelian gauge theory, right? A bit like chromodynamics, quantum chromodynamics instead of electromagnetism. And non-abelian is usually a bit more interesting and rich. But usually, it turns out that if you try to prepare such non-abelian states via measurement, naively, I think I was taught that it shouldn't be possible. Okay, why is that? Why should it be more difficult to create non-abelian topological states? Well, let's actually go back to the toric code case that we saw that worked, right? And if we just think about it from physical terms, what are we actually doing? We start with a product state, and we actually then measure so-called, and the physics you speak is, we measure where the E anyons are. That's the physical interpretation of this four-body term you were measuring. Basically, the plus or minus one tells you you have no E particle or you have an E particle in your gauge theory. But because all of these are abelian particles, you can cleanly pair them up in finite time, and then you get a clean Z2 topological order, is the fancy word, basically a toric code wave function. But if you try to mimic the same step for a non-abelian state, you start with a simple product state, you try to measure where the non-abelian charges, you will get some definite answer from your quantum measurement. But it turns out that once you have non-abelian anyons, you can't pair them up in finite time. In other words, in terms of string operators, even though abelian anyons can be paired up in a finite depth string operator, non-abelian anyons require a linear depth string operator to pair them up. So now you're stuck. You can't polish up your state. You can't get a clean non-abelian state. I think that was the intuition for I thought it was hard to create non-abelian states via measurement. So what's the point? Well, I was trying to convey to you that we can apply this general map. And it turns out that allows us to create certain non-abelian states. And the reason is actually quite simple, right? You can apply your map on anything, which means you can do it multiple times. You can start with a product state, apply the map once, get something like the toric code, okay? But now that can be the input state of another application. So you can keep increasing the complexity of your state. And it turns out that can lead to something non-abelian. For example, you might start with a product state and create something called a generalized version of the toric code. For those of you not familiar, let me stay a bit vague to not get lost in the details. But some of you might know basically a Z3 toric code. It's basically an emergent gauge theory for Z3 symmetry rather than just Z2. But basically still relatively simple type of topological order. The point is this state has a physical symmetry, which is charge conjugation. The emergent particles can be exchanged by a physical Z2 symmetry, because charge conjugation symmetry. And now we apply the same gauging map again for this Z2 symmetry. So it's a two-step process. And it turns out, at the end of the day, you get a non-abelian gauge symmetry, S3. And if you're wondering why is it non-abelian, just think of the symmetry group of this triangle, which is S3. And in some sense, it has two abelian parts to it, right? The rotational triangle is a Z3 symmetry, and the mirror is a Z2. But even though they're individually abelian, their interrelation is not abelian. They don't commute. Those two operations don't commute with each other. And somehow the same appears in this physical context, that because we gauged, even though at every step we only gauged an abelian symmetry, their interplay is non-abelian. And it gives us a gauge theory where the symmetry group is that of the triangle. And this can be generalized this can be generalized to all groups which are so-called solvable. What it just means is any group that kind of looks like this, where it's a finite number of abelian groups put together, so-called extensions, basically things that look like S3 in that sense, by using multiple applications of this map. But we also think, so far it's fact, but we also think that you can't do anything more, sadly. And sadly, most groups are not solvable. In particular, we have a no-go conjecture. It's kind of we have a few arguments, but it's not a solid, there's one possible loophole, so that's why it's not a theorem. But we have a plausibility argument and a no-go conjecture that measurement cannot prepare, say, emerging gauge theories for a non-solvable gauge group. Why am I putting the picture of Galois there? Those kind of same notion was used by Galois to prove that you can't solve quintic polynomials, right? If you have a polynomial of degree 5 or more, it turns out you can't write it efficiently, because you can't basically solve it in terms of radicals, which has to do mathematically with this effect that A5, alternating group of symmetrizing 5 elements, is a non-solvable group. Somehow there seems to be a surprising link there, potentially with Galois theory and not being able to pair certain states with measurement. Over?
An example of one type of topological order where you can prove you can't prepare it? I mean, this conjecture is very general,
right.
But maybe say Fibonacci or so, you can prove it that it's impossible.
Yeah, you would like, sadly not. It needs to be done.
Because I think things like Fibonacci anyons have the strange property that you can have a single anyon on torus and things like that. And there it seems to be hard to imagine what you would pair it up with.
Oh, no. Okay, that's not enough, because some of the cases we can do, you also have that property. So that's not going to be the obstruction.
Okay, so even if the measurement only needs a single anyon, there's a way to remove it in the end.
Yeah.
Sounds puzzling. Okay, anyway.
Well, okay, but you can. But yeah, can have to. Yeah.
If you were given multiple copies of, say, Fibonacci, something that you can't prepare, you do something like a twisted double Fibonacci through what you do.
So you're starting with something I can't prepare?
Yeah, you're given something you can't prepare, but let's say you're given a few copies of it.
Yes.
Can you then gauge certain abelian symmetries out of it?
You can, but the statement is you won't be able to leave that class. Like, that'll never end up in a trivial sector. You can do this. Yeah, okay. If the question is just, if I have two Fibonacci's, can I gauge a Schwab symmetry or something like that? Yeah. So you can still explore things in the same, we call them measurement equivalent phases. But yeah, we can't get to the starting point from just measurement. But indeed, if you can get it from some other means, measurement can be used to transform it and get some twisted versions and whatnot. That's a nice point, yeah.
We have a question online. So
Great.
Your explanation suggests that you assemble groups through conjugation, so semi-direct products. Does this still work for solvable groups that aren't semi-direct products? For example, a quaternion group, which is solvable but can't be assembled from simpler groups.
That's a great question, actually. Who's that from? I see. Yeah, it's a great question. So indeed, it's a good question, and you can still do the cases that are not just semi-direct products. The key there is to slap on an SPT. So I think whoever may be asking the question can understand that if I say, if you slap on an SPT before you do the gauging, you can get twisted gauge theories that way, which get around this issue. But so indeed, you can get all solvable groups without that extra restriction. But thanks for the question. Good. So then, just to wrap up, so what we see so far, for example, if you have one layer of measurement, you can compare Torre code. And if we did multiple layers of measurement and feed forward, like 2, you get S3, non-abelian stuff. You could ask, what is the hierarchy of states involved here? For example, if I only use one layer, can I get something more interesting than the Torre code? Can you kind of get a non-abelian state from only using one layer of measurement? There's also a practical question, right? Because it's still costly to do multiple layers of measurement. And I think, looking at the clock, let me skip ahead. Let me just not talk about it, just say the answer is yes. It turns out even a single layer of measurement can prepare certain non-abelian states. In fact, Norbert, even these have the property with a single anyon on the torus. So it's hard to have a parallel intuition for which things are hard to do. And we need to have a better understanding for what is really the obstruction. And so sorry for skipping ahead of this. Let me get just to the summary here of the picture that emerges is the following. Right? So in the absence of measurement, we know there's many different types of topologically ordered states of matter, which cannot be connected by a finite depth unitary, like product state is distinct from Torre code, is distinct from double semyon. But measurement gives us a hierarchy on the structure. In particular, using measurement, we already saw that product state can be transformed to Torre code. Okay? And you can create other kind of state, for example, S3, stuff with a triangle. We can do with 2 layers of measurement. That's what this double line signifies. With other types of non-abelian states, like D4, you can compare with one layer of measurement. Or same with quaternions that the question was about, quaternion topological order. You compare with one layer of measurement. But we also think there are really hard different lines of states you can't get from measurement. Like Fibonacci anyons, we think it's impossible in finite time to get it with measurement. But then as Roger was asking, you can still explore how things that are both impossible are related to one another. For example, A5 and S5 are different, and are both distinct from a product state, but are related to one another by measurement. So there's this hierarchy of states to further explore that we're just getting a glimpse into, but I think we don't yet have a full understanding, and in particular, no hard proofs about no-goes to really prove that some of these red boxes are generally distinct from the product state. So that brings me to the end of my talk. So in the first part, we saw experimental protocols for creating such states in experiment. And the second, kind of more theoretical aspect, we were seeing what can you imagine doing in the future. And then, of course, there's a variety of questions to further explore. For example, like Norbert was asking, can we prove any rigorous no-go arguments? And at the moment, there's 0. It'll be very exciting to, well, okay, no 0 that I'm aware of, but who knows, maybe someone here is about to post a preprint, so I don't know. And it will be interesting to try to relate this hierarchy that we operationally see in terms of measurement to also the computational power of these states, because some of these states are more powerful than others for quantum information purposes, but a tight link has not really been made. Can you compare different types of states like critical states? And of course, it'll be exciting to actually create these non-abelian states in experiment using these kind of tools. So that's another exciting direction to work towards. So with that, let me end and just thank all my collaborators and thank all of you for your time and attention.
Okay, thanks a lot for an interesting talk. We have some questions. Yeah, Tibor.
So there are other kind of gauging maps that can prepare things like fractons instead of toric code. Have you thought about doing those?
Yeah, it's a great question. So indeed, here I was fixing on gauging global symmetries. But for fractons, you just want to gauge a subsystem symmetry. But the method works as such. Yeah, we discussed a few examples, but not very extensively. But so it would be interesting to see, if there's something, right, kind of a qualitatively new aspect once you start considering about the subsystem symmetries. But in principle, there will be a kind of a streamlined approach to explore that. Yeah, thanks.
Suppose, so what about this algorithm to sort of create any sort of non-abelian theory? Suppose sort of you mentioned that the problem is that sort of you need a linear depth circuit to sort of match up these anyons, right? But sort of suppose it's possible to create more anyons, right? I don't know, like maybe you can sort of measure a patch of your system, sort of disentangle it, and re-entangle. So you probabilistically produce more anyons. Sort of if you have sort of your anion defects, couldn't you just sort of produce more anyons right next to them and then pair them up?
That's a great.
Give you an algorithm.
That's a great method to try to do, kind of, right, having two far away anyons. And now imagine creating a bunch of pairs at the same time, right? And then trying to pair them, like statistically try to pair things up basically in parallel, right? And try to hope that you fuse to one, right? So in certain groups, that's bound to work. In particular, nilpotent symmetries, you can show that the sequence always has to end in finite time. So there you guarantee that it works. But those sadly are a subset of solvable systems, so that directly doesn't work. And we think that, for the general case like Fibonacci, you're probably gonna get stuck. As in, it's not clear that it'll actually end up fusing to identity in finite time. Okay. One kind of tangent question there, or I think that would be nice to be explored in that context, like you're saying, is so far I'm focused on things I can do with probability 1.
Yeah, exactly.
Yeah, which is kind of a nice starting point, but right, it's a bit unnatural as well, right? You might be happy with like a finite, right, success probability. So then I agree, it would be interesting, and maybe in that context one could try to explore these kind of probabilistic schemes. And at the moment, I think there's no results as such, but it would be good to think about more. Yeah.
So correct me if I'm wrong, but it seems like this set of states that you can prepare with measurements in a shallow circuit can also be prepared as PEPs.
Good. Yeah.
So then it sounds like the states that the quantum computer are having trouble preparing, it's the states that they can prepare are also seem like the class of within PEPs.
Okay, there's
so
a few.
Don't you want to move past, you know.
Okay, yeah. There's a few things to pick up on there. So one thing you can show in general, anything you do with finite time with measurement is automatically a subset of PEPs. Right? It's in the name, right? PEPs is about stuff that's local entanglement and projection, which is like a forced measurement. So it's PEPs is even bigger than anything I can do with this in finite time. But the point, okay, first of all, PEPs doesn't automatically mean you have access to all the things you would like, right? Because contracting can be difficult. So there's that route that it could still, if I can create any PEPs, actually that will be pretty nice, I think, for certain tasks. But secondly, as also kind of a remark in the previous talk, right? It's not always about kind of computing a property of that state. It's about having that quantum state. And of course, then it's very much a context-dependent question of why do I even want to create a state in the first place, which is a fair question. That depends a bit on the, if you're trying to study many-body physics, maybe this is supposed to be like the initial state for then doing some many-body physics, right? Or maybe are you going to use it as a quantum error correcting code or whatnot? That depends, right? And eventually might do stuff that you can't have done classically. So then it becomes a bit context dependent. But there is an important distinction to be made about being able to create that actual state, right, in the lab, versus being able to compute certain properties of it. Yeah. But,
we have a question.
Oh, yeah.
I guess builds on that. The protocol is similar to the quantum error correcting code procedure for logical qubit. Does the result here have any implications on quantum error correcting code? And that's in Sheng Shuang.
Yeah, it's a great question. So indeed, in some sense, what I'm talking about is it's even like the baby steps for quantum error correcting. Like being able to do this, you better be able to do it if you want to do error correction, in a sense. There's some slight distinctions there. Error correction, sometimes you're happy to do stuff in post-processing, whereas really I want to get it deterministically. So there's already a slightly more challenging aspect to the way I was asking the question. But nevertheless, there's a very tight connection. And so indeed, being able to deterministically create Tory code is likely to be the same set of ingredients you would need, or the minimal set of ingredients you would need to actually eventually do surface code with any type of gate. That's not just Clifford. But let's see, what other point did I want to make there? Oh yeah, another point is usually these kind of error correcting codes are based on these abelian states. At least, I might easily not know everything that has been explored. But now that we can see that we can create these non-abelian states in finite time, maybe it invites thinking about their quantum error correcting properties. And it's not actually trivial to transform what we have into a quantum error correcting code. So that itself is actually one of the bulletin points there. So it invites some new questions to ask in the non-abelian case, I would say. Thanks for the question.
We still have time for maybe 3 questions, so in the back.
Yeah, so thanks a lot. So a lot of what you do taps heavily into the toolbox of measurement-based quantum computing. So I was wondering if you want to do sort of now operations on top of these states that you prepare, do you think it would be sensible to use more of those tools or to just like perform gates on those?
Well, the last part was about doing Clifford.
So let's say you want to do something with the states that you create. Do you think it makes sense to, again, use measurements to do that? Or would you rather just apply gates?
Yeah, it's a great question. Realistically, you'd probably want, it really depends on what, there's many different ways you could try to go with it. But if you want to use it in the kind of quantum information processing perspective, right, it's kind of what your question, I think, is leaning into. In, say, the non-abelian case, if you only use unitary gates to then move the non-abelians and braid them around, that is still, you have the linear depth issue. So then you could try to use measurement to more quickly move them around. So that seems like a likely use as well. So that's kind of one direction where you definitely indeed want to use the same ingredients later on. But more generally, I think maybe there's just more thinking about what exactly what do you want to do with it and what are the tools you want to use. So I can just give you one example, but much more, it's good to think about it more. I think it's good, yeah.
Diagram on the hierarchy of states, there was this one box which had a different line style, the spiral.
Oh yeah.
Is that intentional?
It's intentional. Right, sorry, it was non-legend. Well spotted. So this nice, more funky line style refers to the fact that, as you can see here, I'm talking about a chiral state, and we probably don't think that a finite depth unitary circuit and measurement can prepare it because, kind of related to what I was saying before, if you could, I would have gotten a PEPs for it, which we think probably doesn't exist, right? But the catch, so this extra funky dashed line, what it means is you can do it in finite time if your unitary gates have exponential tails. So it's basically the local stuff generated by local Hamiltonians rather than strictly local circuits. Yeah, thanks for the question.
Okay, and time for one last question. Yep.
You have these like hard red boundaries on the.
Yeah.
But presumably you could always go to a product state.
Yeah, great.
It's just like a partial order on.
Yeah, exactly. That's why. So I also didn't read out loud this measurement equivalence phase, but the red boundaries are different measurement equivalence phases where we define an equivalence class as we say two states are in the same measurement equivalence phase, A and B. If you can go from one to the other and back, because indeed you can always you can just take any of these states and measure everything. I get a product state. But someone will want to maybe one notion of equivalence is saying if you can go both ways. But indeed, there seems to be kind of a partial ordering. And even that structure is not always, yeah. I also don't know the full partial ordering structure. Of course, there's always everything goes to the trivial state, but more generally, it would be nice to think about that as well. Yeah.